অ্যাটেন্ডেন্স দিয়ে দিয়েছো? হ্যাঁ, কখন দিলে? এই দিব্যনন্দন, অ্যাটেন্ডেন্স দিয়েছিলে? তারপরে খোলেনি আর? আমি আবার দৌড়ে দেখে আসি ক্লাস। অ্যাটেন্ডেন্স হচ্ছে, দিয়ে আসো।
Hello.
Hello. Hello, am I audible? Just a minute. Hello. Am I audible? Yeah, good evening. So Is there any question from the last class? Let me share my screen. If there is any question from the last class, you can ask. So I think let me just check one thing. This was class 9, right? So this class 10th class today. Mm, 30th September, right? So today we will solve few problems from semiconductor, as I guess Renuka Devi was pointing out in the last class that we need to solve few problems on the semiconductor. So we'll solve few problems from the semiconductor. So I think everyone knows about what is semiconductor and p-type semiconductor, n-type semiconductor. So I'm not going into the details of the theory. I'll basically solve few problems, and whenever some formula I'll write them out. So let me start with. So okay, so this is the first question I'm going to solve now. In intrinsic gallium arsenide, the electron and hole mobilities are 0.85 and 0.04 meter square per volt second. And the corresponding effective masses are 0.068 m naught and 0.5 m naught respectively. Where m naught is the rest mass of an electron. And given the energy band gap at 300 Kelvin as 1.43 electron volt, determine the intrinsic intrinsic carrier concentration and conductivity. So this is the question. Sorry. So this is a question from semiconductor chapter. So in the question I will read again. In intrinsic gallium arsenide, the electron and hole mobilities are 0.85 and 0.04 meters square per whole second respectively, and corresponding effective masses are, so these are the masses of electron and hole, where m naught is the rest mass of an electron. So given the energy band gap at 300 Kelvin as 1.43 electron volt, determine the intrinsic carrier concentration and conductivity. So first I will write what is given in the question. What is given? First the mobilities are given. So mobilities are expressed in terms of mu. Mu n is the mobility of electron, which is 0.85 meter square per whole second. Then the mobility of hole, which is mu h, this is given as 0.04 meter square per whole second. Then the mass of the electron and hole, they are also given. So mn star is 0.068 m naught and mh star is 0.5 m naught. Then what we have? Eg and T. So Eg is the band gap. So the band gap for gallium arsenide at 300 Kelvin is given as 1.43 electron volt, and the temperature is given 300 Kelvin. So there is the formula. I'll write down. Let me write down the formula. Maybe it is already taught in the class. So the intrinsic conductivity, intrinsic carrier density carrier concentration is given by Ni equal to two into 2 pi kVt into T by h square to the power 3 by 2 into mn star mh star to the power 3 by 4 into e to the power minus Eg by kVt. So this is the formula to find out the intrinsic carrier density for a extrinsic semiconductor. So in the question already mn, mh and Eg and temperature all are given, and the rest of the things are constant. So in the question h, so you know that h equal to 6.626 into 10 to the power minus 34 joule second, and kV is equal to 1.38 to 10 to the power minus 23 joule per Kelvin. Sorry. So you put this put all the values in the formula Ni. So you might need to memorize this formula. You need to memorize. So you will find it any standard book. So put all the values and calculate the answer. Two into 2 pi into kb 1.38 into 10 to the power minus 23 to T is 300 Kelvin, sorry, divided by, so this 2 is outside, divided by h square, which is 6.626 to 10 to the power minus 34 square, this whole to the power 3 by 2 into mn star into mh star. So mn is 0.068 into mh star, mh is 0.5 into m naught square. So m naught is the mass of electron. We can multiply it later also, or you can multiply it here. So 9.1 into 10 to the power minus 31 kg, this m naught square, right? Yes, so this is square into to the power 3 by 4 into exponential minus Eg. So Eg is given in 1.43 electron volt, 1.43 electron volt, and you may remember this, that kb is kbt is equal to 0.026 electron volt if T equal to 300 Kelvin, because this information is needed almost in every question. So you can remember this, that kbt is equal to 0.026 electron volt when T is 300 Kelvin. So we will write it as 0.026, sorry, 2 kbt, the formula was 2 kbt, so here it will be 0.026 into 2. So you need to calculate this in your calculator and let me know the answer. Look, everywhere we have used SI unit in terms of joule, but in the exponential we have written the energies in electron volt. So in the exponential it does not matter, because in the denominator and numerator both are electron volt, so this will cancel out and it is just a number, so it does not matter what unit you choose. So we can calculate this, let me check. Okay, so 2 into 3.142 into 1.3. Please everyone calculate this, because this is a big expression and we might make mistakes. 3.142 into 1.38 into 300 divided by 6.626 square, so 59. So you can do it step by step. 2 into this value is given as 59.26 into 10 to the power. So okay, this can be also determined. So 23 minus 34 into 2, 45 to the power 3 by 2 into 0.068 into 0.5 into 9.1 square. So this is 2.81 into 10 to the power minus 62 to the power 3 to the power 3 by 4 into exponential. So exponential minus 1.43 divided by 0.052. So exponential of this value is 1.13 or 1.14 into 10 to the power minus 12. calculate this, then this will be, so 59.26 into 10 to the power 45 to the power 3 by 2. This is just 1.44 into 10 to the power 17 into, now there is 2.81 into 10 to the power minus 60 to the power 3 by 4. So this is 6.86 into 10 to the power minus 47 into 1.14 into 10 to the power minus 12. So keeping everything together, we will get 1.44 into 6.86 into 1.14 22.5 into, now 70 minus 47 minus 12, 10 to the power 11 meter cube, or it is so it can be written 2.25 into 10 to the power 11 meter cube inverse. So this is the answer I got. What about others? Did you calculate it and find the same answer? Hello, can anyone confirm that if you have got this answer or some other value?
Sir, it will take time.
Okay. So calculate it and tell me what is the value. So in the semiconductors problem, you have lengthy calculations, so you have to do it. There is no other way. If you find the answer, then let me know. Yeah, 10 to the power 12. Sorry, is because it was 22.5, so it is 10 to the power 12. Right. So one has already calculated. So we can move to the next part of the problem, where we need to calculate the conductivity also. So we found the intrinsic carrier concentration. Now we need to calculate the what is the conductivity. So the conductivity formula is given by, for a semiconductor, the conductivity is given by sigma equal to, now you know the intrinsic carrier concentration, so you can write the conductivity in terms of intrinsic carrier contribution, which is NIE into mu n plus mu h. So all the values you already know. Ni you have calculated, which is 2.25 into 10 to the power 12. E is 1.6 into 10 to the power minus 19, and mu n and mu h both are given in the question, 0.85 and 0.04. 0.85 plus 0.04. So So let's calculate it. It will be 2.25 into 1.6 into 0.85 plus 0.04. So 3.2 into 10 to the power minus 7 ohm meter inverse. So this is the conductivity. So we know that for basically for a metal the conductivity sigma is given as Ne mu. So where N is the carrier concentration, is the electric charge or charge of this particle, and mu is the mobility. So for semiconductor it changes because the mobility of electrons and holes are different. So for semiconductor, and this is the formula for the conductivity. Is there any question? Did you get the same answer for conductivity? So you need to remember these formulas because this will be used in the next problems also, and those problems you will be solving by yourself first. So this is one formula, there is this formula. So let's say this is equation 1, this is equation 2, and note this value also, that for 300 Kelvin kBT is 0.026 electron volt. If you know this, then you can use it any problem. You did not need to calculate it, you just use this value. If has everyone done this? So let's move to the next question then. Question number 2. Calculate the effective density of states in the conduction bands of gallium arsenide at temperature of 300 Kelvin. The effective mass of the electron is 0.067 times mass of the free electron mass, and given Planck constant H 6.6 into 10 to the power minus 34 joule second, then mass of free electron
हम निकल रहे हैं, लैब से निकल रहे हैं।
Mass of free electron M is given as 9.11 into 10 to the power minus 31 kg, and Boltzmann constant is Kb equal to 1.38 into 10 to the power minus 23 joule per Kelvin. So these are given in the question, and also this is a multiple choice question, so there are 4 options also. 2.17 into 10 to the power 20 meter cube inverse. Option B is 3.15 into 10 to the power 22 meter cube inverse. Option C is 4.39 into 10 to the power 23 meter cube inverse, and option D is 5.75 into 10 to the power 26 meter cube inverse. So calculate this for gallium arsenide. So you might need to use that formula for density of states function. So let me write down the formula here. The effective density of states in the conduction bands is given by NC, which is equal to 2 into 2 pi mn star kVt divided by h square to the power 3 by 2. So when I wrote this formula equation 1, so it is actually coming from that effective density of states. So you can write this Ni. If I add one more line, where do I, so I am writing this here. So basically Ni, the intrinsic carrier concentration, is given by Nc Nv to the power half into e to the power minus Eg by 2 kT. So this Nc is the effective density of states of conduction band. This is the effective density of states. Density of states of conduction band. And this is the effective density of states of valence band. So that's why they are expressed in terms of Nc and Nv. So this after putting this formula of Nc and Nv, we will get equation 1. So this is even before equation 1. So that is the expression of Nc. If you put this down, so let me write it as equation 3. Similarly, you will get an expression for Nv also, and putting Nc and Nv in this expression, you will get equation 1. So since you know Nc, now put the values of Mn star, kVt, h square, everything is given in the question. You will get Nc. The question was to calculate the effective density of states in the conduction bands of gallium arsenide at a temperature of 300 Kelvin. So since everything is already given, you can definitely calculate. So first write down what is given in the question. Mn star is given, which is 0.067 times 067 times m naught. M naught is electron mass, so it will be 0.067 into 9.1 into 10 to the power minus 9.11 10 to the power minus 31 kg. Then kBt is given, or kt, which is 1.38 into 10 to the power minus 23 joule per Kelvin. H is T is 300 Kelvin. So kBt or kt is 0.026 electron volt. I already told that for if T is 300 Kelvin, then kt is equal to 0.026 electron volt. But I don't think it is needed here because yeah, so everything is in joule. Okay, and H is 6.6 into 10 to the power minus 34 joule second. So these constants are given in the question. Now you need to put all this down in equation 3. Then NC will be 2 into 2 pi 3.142 into Mn star. Mn star is 0.067 into 9.11 into 10 to the power minus 31. kb is 1.38 into 10 to the power minus 23 into 300, which is divided by 6.6 into 10 to the power minus 34 whole square, because h square is in the denominator, and this to the power 3 by 2. Now please calculate this and let me know what is the value you are getting. We have 2 into 3.142 into 0.067 to 10 to the power minus 31, 1.38 into 10 to the power minus 23 into 300. So, and it is divided by 6.6 10 to the power minus 34 square. So someone has already calculated and saying option C is correct. Yeah, so it will be 2 into 36.41 into 10 to the power 14 to the power 3 by 2, and that is equal to 4.39 into 10 to the power 23 meter cube inverse. So this matches with option C. So this is the effective density of states in the conduction bands. So option C is indeed correct.
Sir, what is the formula for effective density for valence band?
Yeah, I'll write down the formula for valence band also. So let me. Okay. So where did I write? So only Mn star in the place of Mn star, it will be Mh star. So N V equal to 2 into 2 pi mh star kt divided by h square to the power 3 by 2. So this is the effective density of states for the valence band. So you can refer to as equation 4. So equation 3 I have written for effective density of states of conduction band, and equation 4 is effective density of states of valence band. So only in the place of mn star you will replace it by mh star. So the effective mass are different for electron and hole. So let me write down this. So option C is correct, right? Options C option is correct, and this is the formula for effective density of states. Effective density of states of conduction valence band. Now so if it is clear, let me move to the next question. Or is there any problem or any doubt? If there is no doubt, then let me write down the next question. This was question number 2, so this is question number 3. Calculate the thermal equilibrium electron concentration in silicon at temperature T equal to 300 Kelvin for the case when Fermi energy level is 0.22 electron volt below the conduction band energy. The value of NC which is also the effective density of states. So NC is called the effective density of states in the conduction band. For silicon at temperature T equal to 300 Kelvin. Kelvin is 2.8 into 10 to the power 19 centimeter cube inverse. And in the question this Boltzmann constant is given. So the Boltzmann constant is, so I will not write this constant value from the next question because you already have the values of these constants. So 23 joule per Kelvin. Now again this is MCQ type question, and this is the options. 1.12 into 10 to the power 22 centimeter cube inverse. If you can do it, then please start doing. I'll write down the options. 3.12 into 10 to the power 20 centimeter cube inverse. Then option C is 7.19 into 10 to the power 19 centimeter cube inverse, and option D is 5.73 into 10 to the power 15 centimeter cube inverse. So the question is calculate the thermal equilibrium electron concentration in silicon at temperature T equal to 300 Kelvin for the case when Fermi energy level is 0.22 electron volt below the conduction band energy EC, and the value of NC, which is also known as the effective density of states in the conduction band for silicon at temperature T equal to 300 Kelvin is given. So for this you will need to use that formula that the okay, so I'll write down. So there are a lot of formulas actually you need to memorize. So the thermal equilibrium concentration in terms of the effective density of states of conduction band is given by NC exponential minus EC minus EF divided by kVt. So this is the formula of the thermal equilibrium concentration in terms of the density of states, in terms of the electron density, effective electron density of states. So you can refer to that equation 5. So everything is given in the question, and using this information, using this equation 5, please calculate this answer of this question. Okay, and also one said that option D is correct. What about others? Yes, I think option D is correct because everything is given in the question. You just put them in the formula and calculate it. What is given? So first write down what is given in the question. NC is given, so you need these values to calculate n. So NC is 2.8 into 10 to the power 19 semicolon inverse. Then EC, so EC minus EF is directly given because it says that for the case when Fermi energy level is 0.22 electron volt below the conduction band. So Fermi energy is, that means EC minus EF equal to 0.22 electron volt, because it is already written in the question that the Fermi energy is 0.22 electron volt below the conduction band. So Fermi energy is below the conduction. If it is the conduction band, then the Fermi energy is there. This is EF, this is EC, and that gap between these two is 0.22 electron volt. And KBT is, so here also T is 300 Kelvin. Is it? Yeah, T is 300 Kelvin. So KBT is 0.026 electron volt, as I have already told. Now you need to put them in the formula. So 2.8 into 10 to the power 19 into exponential minus 0.22 divided by 0.026. So upon calculating this, you will get 2.8 into 10 to the power 19 into this value is 2.1 into 10 to the power minus 4. So 2.8 into 2.1, which is 5.88. It is 2.8, right? Yeah, 2.8. So this is 5.88 into 10 to the power 15 centimeter cubed. So is it the value already all of you have got? Wait a minute. So minus 0.22 divided by 0.026. 2.9. Yes. So this is the value. So it is almost equal to the option D. Correct option is Is it clear to everyone? If not, you can ask. Since there is no question, we'll solve the next question. Hello, is there any question? So this is almost a similar problem. By the way, is this question already solved in previous classes? Can anyone answer this? Am I repeating these questions or what? You can tell. Then we can solve new problems if these questions are already solved. Determine the thermal equilibrium concentration in gallium arsenide at temperature T equal to 300 Kelvin for the case when the Fermi energy level is 0.30 electron volt above the valence band, energy EV. The value of band gap energy which is given by EJ of gallium arsenide at temperature T equal to 300 Kelvin. Temperature T equal to 300 Kelvin is 1.42 electron volt. And NC, so what is NC? NC is effective density of states in the conduction band. For gallium arsenide at temperature T. T equal to 300 Kelvin is 4.7 into 10 to the power 17 centimeter cube inverse. So the question is, determine the thermal equilibrium concentration in gallium arsenide at temperature T equal to 300 Kelvin for the case when Fermi energy level is 0.30 electron volt above the valence band energy EV. The value of band gap energy of gallium arsenide at temperature T equal to 300 Kelvin is 1.42 electron volt, and NC, which is the effective density of states in the conduction band for gallium arsenide at temperature T equal to 300 Kelvin is 4.7 into 10 to the power 17 centimeter cube. So you need to find the thermal equilibrium. So it is the same question of the above. A is 6.53 into 10 to the power 13 centimeter cube. So these are the options. Option B is 5.73 into 10 to the power 3 centimeter cube. Option C is 0.0779 centimeter cube inverse, and option D is 0.6.
Hello, sir.
Yes, hello. Hello. Is there any question? Hello, is anyone asking any question? If you have any doubt, you can ask. Okay. So yes, so these are the options. So again, you need to use this formula, equation 5, and find out the answer of this problem. So this is almost the same question of as the above question. Please find out and let me know. There are so many problems we need to solve, so please do it early.
Hello, sir. Good evening. Hello, sir. Good evening.
Yes, good evening. Hello, yes.
Hello, sir. Good evening.
Okay, so hello, logo. Do you have any question?
Hello, sir. Good evening. Hello, sir. Good evening.
Hello.
சார் ஒன்றும் இல்லை சார் தம்பிங்க.
I can't understand this language. You need to speak in
Hello,
English.
sir. Good evening.
Shall I
Logu logu.
mute her?
Hello, sir. Good evening.
So I think I have,
Sir, you can mute, sir.
yeah, I have muted her. So let me know if you find the answer. Hello, have you calculated? No one calculated? Please calculate this and let me know the answer. It's the same problem like the previous one. It should not be difficult to solve. So it's almost so much time you have already taken. So what is the problem in solving this problem? Can anyone tell me what is the doubt or what is the issue that you cannot solve this problem but the previous one you could solve, because it's the same problem.
Thing given here given two band gap value. Which one taken, sir?
Okay, so what is given is, for the first case, the case when Fermi energy is 0.30 electron volt above the valence band. So in the previous question it was said that the Fermi energy level is 0.22 electron volt below the conduction band. So you need EC minus EF. Here also the formula is same. So the formula will be N equal to NC into exponential minus EC minus EF divided by KBT. So this is the formula for calculating this thermal equilibrium concentration. Now in the previous problem, let's say this is the valence band, this is the Fermi energy, this is the conduction band. So
Hello, Max. Good evening.
where is logo? Yes, I did.
Hello, Max. Good evening.
I think I have muted her.
Hello, Max, sir. Good evening.
Yeah. So
Come on, hello, Kulu.
I don't know who's this.
I think now only muted, sir.
Yeah, I have muted her. Okay. So yeah. So let's say this is the conduction band energy, this is the valence band, and and somewhere between uh, there is the EF. So in the previous question, it was given in the question 0.22 electron volt. It was directly given, but in this question it is not directly given. You need this. Sorry. Yeah. So you need this energy gap. But what is given in the question? This total energy gap is given Eg, and it says that the Fermi energy is 0.30 electron volt above the valence band energy. So this energy is given. Let me use the different color. So this energy and this energy, these two energy are given. So you can definitely calculate this energy from by subtracting the Eg from this. So what I am trying to say is EC minus EF is actually equal to Eg minus this 0.3, what was this, 0.30 electron volt. 0.30 electron volt. So that is what is AC minus EF. It is not directly given. So EG is 1.41, sorry 1.42 minus 0.30. So let me add, someone is trying to come. Yeah, this electron volt, 1.12 electron volt. This is EC minus EF. Now you need to put this in the formula.
Sir, option B correct.
Option B. Okay, so let's calculate it. We are almost there. So NC is given. NC is 4.7 into 10 to the power 7 into 10 to the power 17, right? 10 to the power 17, yeah. Into exponential minus EC minus EF is 1.12, and for 300 Kelvin, temperature is 300 Kelvin, so KBT is 0.026. So calculate this. Let me calculate it. So this is minus of 1.12 divided by 0.026. So it is 4.7 into 10 to the power 17 into 1.96 into 10 to the power minus 19, and this will be equal to 4.7 into 1.96 divided by, so it is 0.09 something like this, 0.
Actually, sir, none of these answer coming.
Yeah, I think I am getting 0.092. What about others? Are you also getting the same answer?
Yes, sir.
Yes, this one true.
Yeah. So it is actually so okay. None of the option is correct, but still it's close to option C. So I think it will be option C, or maybe let's not pick option C. Just this is the answer. 0.092 centimeter cube. Did you understand how I calculated EC minus EF from the given information in the question? Okay, so if there is no problem understanding this, so let's then
Sir, I think directly are you given 1 point EG value 1.42 minus 0.30 means coming that 5.8 something, sir.
sorry, 1.42 minus 0.30 is 1.12, right? So EC minus EF is this one, this value, and this value I have calculated from this EG minus 0.30. Is it not clear?
Clear, sir, clear.
Okay, okay. So this problem we were solving. Okay, so then we have a problem similar to this one. This question number 4. Okay, so this is wrong. Let's solve question number 5. So these kind of problems are there in your assignment 9. I think the due date is also over. Now you can solve. Did you guys submitted the assignment already? So if you have submitted, then definitely you must have solved this kind of problems. So determine the thermal equilibrium hole. Determine the thermal equilibrium hole concentrations in gallium arsenide at temperature T equal to again it is 300 Kelvin for the case sorry for the case when Fermi energy level is energy level is 0.30 electron volt above the valence band energy EV and the effective density of states in the valence band which is also denoted by NV for gallium arsenide at temperature T equal to 300 Kelvin is 7 into 10 to the power 18 centimeter cube inverse and kV is given. And the options are 1.5 into 10 to the power 10 semi cube inverse. Option B is 6.5 into 10 to the power 13 semi cube inverse. Option C is 9.7 into 10 to the power 16 centicube inverse. D 7.7 into 10 to the power 19 centimeter cube inverse. So these are the options, and I will write down the formula for thermal equilibrium concentration of hole. So previously I have written down the formula for the thermal equilibrium concentration of electron. So similarly the formula is it can be written as P or H, whatever you like to. So let's write it as P, and P is NV into e to the power minus EF minus EV divided by kVt. So this is the formula. Use this formula to calculate the number thermal equilibrium density of hole for gallium arsenide. So Renuka Devi is saying option B is correct. Yeah, so option B is correct for this. So as you can see, everything is given in the question. NV is what is NV? 7 into 10 to the power 18 centimeter cube inverse, and the energy is saying that the when the Fermi energy level is 0.30 electron volt above the valence band energy EV. So EF minus EV is 0.30 electron volt, and the KBT is 0.026 electron volt for 300 Kelvin. So right, put these values, you will get NV, which is 7 into 10 to the power 18 into exponential minus 0.30 divided by 0.026, and this answer to this question, this expression is minus 0.30 divided by 0.026 into 7 into 10 to the power 18. So the answer is 6.82 into 10 to the power 13. Which is close to equation option B. So the correct answer is option B. So now let's move to some different questions. So okay, so the next question is almost same. I'll not solve this one. Calculate the intrinsic K concentration. Okay, so this question you can solve. So let me write down this very quickly. Temperature T equal to 300 Kelvin for the case when Fermi energy level is energy level is 0.22 electron volt below the conduction band energy EC. The value of band gap energy Hello. So this is the question. Calculate the thermal equilibrium hole concentration in silicon at temperature T equal to 300 Kelvin for the case when Fermi energy level is 0.22 electron volt below the conduction band energy EC. The value of band gap energy of silicon at temperature T is 1.12 electron volt. The effective density of states in the valence band NV of silicon at temperature T 300 Kelvin is 1.04 into 10 to the power 25 meter cube inverse. Then what is the thermal equilibrium hole concentration? So you can calculate this. It is almost same to this question. So here we calculated the energy, sorry, the thermal equilibrium concentration in conduction band, and in here we are calculating the concentration of hole. So using the same concept you can calculate this. Calculate this and let me know the answer. Harsh, पानी भर के लाना पानी क्या ना मेरा क्लास चल रहा है टाइम 5 मिनट गैप है 5 मिनट नहीं बात okay. So you have calculated and says option A is correct. Yeah. So for this problem, option A is correct. It is same to the last question number 4. So here also you need to calculate NV, sorry, N which is NV into exponential minus EF minus EV divided by KVT. Now if this is EC, this is Fermi energy, and this is EV. So in the question it says that the value of band gap energy is given. Okay, yeah. So the Fermi energy level is 0.22 electron volt below the conduction band energy. So this value is 0.22, and the total EG is also given. So you can calculate what is EF minus EV, which is will be EG minus this 0.22 electron volt, and EG is 1.12. So 1.12 minus 0.22 electron volt, it will be 0.90 electron volt. Now you can calculate this. NV is also given 1.04 into 10 to the power 25 into exponential minus 0.90 divided by 0.026, since temperature is again 300 Kelvin. So exponential minus 0.90 divided by 0.026 is into 1.04 into 10 to the power 25. So it is 10 to the power 9.63 9.63 into 10 to the power 9 meter Kelvin hours. So if we consider the order, then it is near to option A. So the correct answer is option A. Is this clear? If you have any question, still if you have any question, then you can ask me. So let me go to there and stop sharing. So this was some one kind of problem we have solved. You can solve new kind of problems also. Let me share the assignment. Up to this, up to question number 6. Do you have any question? So let me solve few questions from the assignment 9 of your course. So there is this question, or just give me some minute. Yes, so share this. Yeah, let me share the screen again.
Now okay, sir.
Yeah. So this is the question number 7. The resistivity of intrinsic germanium at 27 degrees centigrade is 0.43 ohm meter. Calculate the intrinsic carrier density at 27 degrees centigrade. And at 27 degrees centigrade, consider the mobility Consider the mobility of electrons and holes in germanium are 0.39 meter square per volt second and 0.19 meter square per volt second respectively. So can you solve this? This question is similar to the first question I have solved today. So you need to use the formula of conductivity for for a semiconductor. These are the options. Meter cube inverse. Option B is 4.1 into 10 to the power 17 meter cube inverse. Sorry, option C is 2.5 into 10 to the power 19 meter cube inverse, and option D is 6.7 into 10 to the power 25 meter cube inverse. So can you calculate this using the formula of conductivity? Yeah, so the answer to this question is option C. Let me solve it. So you know that sigma equal to NIE into mu n plus mu h. So I have already written this formula in the first problem. What is given? Given is sigma, and sigma is what? 1 by 0.43, because sigma is 1 by rho, and this 1 by 0.43 ohm meter inverse. Then Ni is what you need to calculate. E is you already know, 1.6 into 10 to the power minus 19 coulomb. Mu n and mu h are also given. So mu n is 0.39 meter square per volt second, and mu h is 0.19 meter square per volt second. So Ni is actually sigma by E into mu n plus mu h, which will be 1 by 0.43 into E, which is 1.6 into 10 to the power minus 19 into mu n plus mu h, that is 0.39 plus 0.19, and that will be, so just calculate this, 1 by 0.43 into 1.6 into 0.39 plus 0.19, that is 2.5, which is equal to 2.5 into 10 to the power 19 meter cube inverse. So this matches with option C. So did everyone get this answer?
Yes, sir.
Okay. So the correct answer is so. If, this was an easy question. So Let's move to the next question. So I'm trying to solve different kind of problems so that you can solve them. A rod of P type germanium 10 millimeter long and 1 millimeter diameter and 1 millimeter diameter has a resistance of 100 ohm. Then what is the concentration, sorry, yeah, what is the concentration of the impurity in this rod? Consider the conductivity in germanium sorry, so I have written always E, it will be A, I think. A. Even in the previous question I guess I have written, no, I have written correctly. So what about the last question? So the conductivity in germanium is only due to the holes for impurity atoms. The mobility of holes in germanium is given by mu h equal to 0.13 meter square by mole second. So this is given, and these are the four following options: 3.24 into 10 to the power 25 meter cube inverse. Option B is 2.10 into 10 to the power 13 meter cube inverse. Option C is 6.12 into 10 to the power 21 meter cube inverse, and option D is 4.47 into 10 to the power 28 meter cube inverse. So these are the four options to this question. What is given? A rod of type P type germanium 10 mm long and 1 mm diameter has a resistance of 100 ohm. What is the concentration of the impurity in this rod? And consider the conductivity in germanium is only due to the holes for impurity atoms. The mobility of holes in germanium is given by this. So it is the important information in this problem is that the conductivity is solely from the holes. So given that information into consideration, please calculate this. Okay, so option C, yeah, yeah. I think option C is correct. How do you calculate this? So R is given, and you know R is equal to rho into L by A. From there you can calculate rho. Rho is RA by L. Now here R is equal to 100 ohm, A is equal to pi into R square, that is pi into, so diameter is 1 millimeter, that is half millimeter, half into 10 to the power minus 3 square, that is pi by 4 into 10 to the power minus 6 meter square. So I have changed this millimeter to meter. Then L is also given as 10 millimeter, that is 10 into 10 to the power minus 3 meter, which is 10 to the power minus 2 meter. So rho will be 100 into pi by 4 into 10 to the power minus 6 divided by 10 to the power minus 2 ohm meter. So it will be pi by 4 into 10 to the power minus 2, it will be, okay, so this will cancels out 10, so 10 to the power minus 2 ohm meter. I have calculated rho. Now we will use the formula that sigma equal to sigma equal to NEE. Okay, so in the question it is written that all the conductivity is coming from the whole concentration. So the sigma of H, which is given as N P, number of holes concentration P into E into mu H. So these values are already given in the question. Mu H is 0.13 meter square, and sigma H. So sigma H is equal to 4 into 10, so sigma is equal to 1 by rho, that will be 4 by pi into 10 square ohm meter inverse. So putting this value, and E is 1.6 into 10 to the power minus 19 coulomb. So if you put all of them, then you will get that P is equal to sigma H by E into mu H, which is equal to 4 by pi 10 square into E is 1.6 into 10 to the power minus 19 into mu H, which is 0.13 meter cube inverse. So let's calculate it. 4 by pi into 1.6 into 0.13, so 6.12 into 10 to the power 21 meter cube inverse. So this is the concentration of hole in this germanium, p-type germanium atom. So the correct answer is option C. Is it clear how did I calculate it? So this is the formula for conductivity coming from the hole. Similarly, you can calculate the conductivity coming from the electron concentration, which is n e into mu n. So this is the formula, and if you want to know the total conductivity, you need to sum this two. So the total conductivity, which is sigma, this is sigma h plus sigma n. So these are the small formulas that will help you to calculate different problems. Now, do you have any doubt? So these are few problems from your assignment 9. So I think everyone has solved and submitted this assignment. So if you have any doubt from that assignment, you can send an email, because today is the time is almost over. I can't start a new problem.
Okay, thanks.
So you already submitted this assignment, right? Assignment 9.
9 submitted, sir. 10 is
Yes,
due
yes.
date is Wednesday.
Yeah, 10 is 10 due date is not over yet. So
Last date was 27.
okay, yes, yeah, I can see that it is 27. So is there any problem from that assignment you want me to discuss? I can discuss. Maybe they will also submit the upload the solution to assignment 9, so you can refer to that. What about
9th solution not uploaded.
yes, yet not uploaded, but they will maybe upload it in the
Okay, okay, no problem. Thank you.
okay. So if there is no question, then we'll end the class maybe. Is there any doubt? We still have 2 minutes, so you can ask if 1 minute. Yeah, so if you have any doubt, you can ask, or else you can leave the meeting. So we'll end the meeting now. So let me stop share this screen. Sorry. So thank you everyone. I'll leave the meeting here. So bye everyone.